Hi, hello. Thermal engineering lesson. Thermal engineering. In thermal engineering, first topic: fundamentals of thermal engineering and laws of thermodynamics. Objectives of this lesson: on completion of this lesson, you would be able to know the definition of thermodynamics and the definition of thermodynamic system, classification of thermodynamic systems, and the definitions for state, path, process of thermodynamic system, quasi-static process, thermodynamic cycle, and thermodynamic properties, and classification of properties, definition of the term pressure, atmospheric pressure, gauge pressure, and define the term volume, and define the specific volume and density. Right? These are the objectives of this lesson. We are going to discuss one by one. So first of all, let me discuss about the thermodynamics. What is thermodynamics? So let us see thermodynamics. Thermodynamics is the science which deals with the relations between heat, work, and the properties of the substances which are connected with the heat and work. Once again, the definition is science or the science which deals with the relations between heat and work and those properties of substances which are connected with heat and work. This is the definition for thermodynamics. And what is thermal engineering? What is, in the previous case, we are going to, in case of thermodynamics, we are going to study the relation between heat and work and the properties concerned with the heat and work. And now let us see what is thermal engineering. It is the field of engineering science which deals with the applications of thermodynamics and its laws, which deals with the applications of thermodynamics and its laws in known as thermal engineering. And also we can define thermodynamics as it is a science which deals with the conversion of energies also. So here in this case, and during conversion of energy from one form to the another form, there are some laws are there, some principles are there, and we are going to use these principles for various engineering applications. In such case, that field of application of thermodynamics and its laws and principles is known as thermal engineering. And the thermal engineering forms basis for study of power plants, refrigeration and air conditioning systems, and even automobile industry also. It is the basis for automobile industry, study of power plants, refrigeration and air conditioning systems, etc. Right? So applications of thermodynamics, wherever we are going to use these the principles of thermodynamics and thermal engineering here. In thermal power plants, energy from coal or oil to convert it into electrical energy. So here is the small thermal power plant in which we are going to use either the coal or oil, and we are going to use this energy of the coal or oil, and we are going to convert this into electrical energy by means of various equipment in various process. So if you say oil or coal are the chemical energy and this chemical energy is to be converted into heat energy, and this heat energy is converted into mechanical energy, and this mechanical energy is converted into finally electrical energy. In thermal power plant, all these conversions will taking place. But here only we are not creating any form of energy, but we are converting. That means thermodynamics mainly deals with the conversion of energies. So here chemical energy is converted into heat energy, and heat energy is converted into mechanical energy, and mechanical energy in turn converted into electrical energy. So this is going to happen in thermal power plants, right? So here you can see these are the various parts of thermal power plant. You see coal conveyor number one. Here is the and stoker, pulverizer, and boiler, coal ash, air preheater, electrostatic precipitator, and smokestack, turbine, condenser, and then thermal transformers, cooling towers, generator, high voltage power lines. So like this, all these are the different parts in thermal power plant, right? Next, applications of thermodynamics in automobile engines. Here in this case, heat energy of the fuel is converted into work energy which drives the vehicles. And the conversion of heat into work depends on the principles of thermodynamics only. So here are the different, as we are seeing in our daily life, we are using many automobile equipment like cars, buses, four-wheelers, two-wheelers, etc. Here also only three conversions. If you see, generally chemical energy is converted into heat energy, number one, and heat energy is converted into mechanical energy, and mechanical energy is converted into electrical energy. See once again, chemical energy into heat energy into mechanical energy into electrical energy. But here in this automobile, only two transmissions are there. That means conversions from one form to another form. That means chemical energy of the fuel is converted into heat energy, and heat energy is converted into mechanical energy in case of automobile. So all these conversions depends on the principles of thermodynamics only. So next is applications of thermodynamics. The working of rocket and jet engines depends on the principles of thermodynamics only. So here you can see jet engines, that means aeroplanes, etc., and have the missiles or the rockets, you can say. Here also all chemical energy conversion into heat, and heat energy then into mechanical energy conversion takes place in even jet engines as well as rocket engines, right? And refrigeration and air conditioning is used to maintain required temperature. Refrigeration and air conditioning is used to maintain required temperature. Let us see. So here are it is the air conditioner, and here is also air conditioner. If you see, here is the refrigerator, and here in this case this will depend on the second law of thermodynamics, and all these depends on that means it will remove heat from a space or the system, you can say, and maintain the temperature below the surroundings. So this will happen in this case of refrigerator as well as the air conditioners, right? So another applications are refrigerator and air conditioning systems to maintain the required temperature. So let us see The definition for thermodynamic system or the simply system. Thermodynamic system or simply system, it is a region in space containing a certain quantity of matter upon which attention is focused for study. Once again, it is the space or the region containing certain quantity of matter upon which our intention or our attention is focused for its study. That is the thermodynamic system, or simply we can say system. And if you see, this is the system, let us take within the dotted lines, this will be the system, and on this system we are going to focus our attention and we want to study about this, its conversions of energy. Then it is a thermodynamic system. And outside this dotted lines, these are dotted lines other than this system is called surroundings, and this outline, this dotted lines is called boundary of the system. Boundary of the system, right? That means our focus is only to study the system, but we are not going to focus our study on surroundings. So that's why this will be the system on which our attention, our concentration is focused on that area in which there is some amount of matter, right? That is the thermodynamic system. And this system may be quantity of steam or mixture of vapor and gas or an ice in a cylinder and its contents. And the system may be some quantity of steam or some mixture of vapor and some quantity of gas also, or sometimes it may be the cylinder also. That is the system, because we are going to study what is happening in the steam due to heat addition, sometimes due to heat rejection, and what going to happen by using the steam in various apparatus, etc. And even for vapor also, and gases are also system, you can say, or sometimes within the cylinder itself of ice engines, etc. So system is enclosed by a boundary. It is enclosed by a boundary of system. So that's why this is called a boundary. That means, as I told you already, the dotted lines. So boundary separates the system from the surroundings. That means the space other than the system is called surrounding. So right. So next, the boundary may be real or imaginary sometimes, or it may be fixed or movable also. The boundary maybe it is real or maybe it is imaginary, and it may be fixed sometimes or it may be movable also. For example, if you say in case of ice engines cylinder, the boundary always changes, it's not fixed due to movement of the piston within the cylinder itself. Whereas in case of turbines, etc., the boundary may be fixed, right? So that is the idea. And anything outside the boundaries is called its surroundings. Next, the classification of thermodynamic system. Here are mainly three types of systems are there. Here are the three types of systems are there. One is the closed system, and another is the open system, and next is the isolated system. One is the closed system, and another is the open system, and next is the finally isolated system. in any system and its surroundings, there is always some energy transactions takes place, and also matter transactions also takes place. That means system consists of mainly two things. One is the matter and another is the energy. Any system, any thermodynamic system consists of matter and then energy. So generally, the system always have interactions with the surroundings. That means they will be they will have transformations. That means maybe energy transformation takes place between the surroundings and its system, and there may be some matter transformations also there between the surrounding and system. So based on the classification, here are the closed system, open system and isolated system. So let us see one by one. Closed system. Work energy is transferred across the boundaries of the system. In closed system, as I told you already, there is a transfer of either matter or sometimes energy to the surroundings across the boundary, or sometimes there is a possibility of matter transmission also from surroundings to system or systems to surroundings across the boundary. Here in this case, closed system, generally sometimes both matter as well as energy can transmit, but here in case of closed system, only the energy transferred across the boundaries of the system. There is no transformation of, there is no crossing of the matter across the boundaries. That is why is called closed system. The system is called closed system if only the heat and work energy are transferred across the boundaries of the system, right? So next is mass content in the system remains constant or remains the same. That means matter remains in the system only. There is no crossing of matter or the mass across the boundaries of the system. That's why the mass content of the system remains the same. The physical nature and chemical composition of the mass can, however, change. Means physical nature changes, sometimes chemical compositions also change, but it is not going to cross the boundaries of the system. So gas in the cylinder is an example of closed system. So here is the system. Let it be the cylinder, and in this cylinder, gas cylinder, there is a gas, and cylinder body itself is the boundary, and it is not going to transfer or cross the boundary. That means gas is not going to transfer or cross the boundaries, but energy can transfer, right? So here is the once again. So here in this case, energy is transmitting, but there is no crossing of the gas in this case. So as the energy is transmitting by informal, actually the gas consists of heat energy, and heat is transferred from outside to the inside of the gas, and this can move this boundary. That means this lid to the upward. So that will happen, but only energy is converted and will be transferred to the surroundings, but there is no transmission of gas to the outside. So this is the idea of closed system. Open system. Here in this case, the system is called open system if both mass and energy. In the previous case, only energy crossing the boundaries of the system, whereas in case of open system, both the matter or the mass as well as energy transfer across the system boundary. Across the system boundary. So in the open system, matter crosses the boundary of the system, and heat and work also crosses the boundary of the system. So best example is motor driven compressor is an example of open system. Motor driven compressor is an example of open system. That means here in this case open system, both energy crosses the boundaries of the system to the surroundings, or sometimes from surroundings to the system, and also matter crosses the boundaries of the system either of the way. So the best example here is the motor driven compressor is an example of open system. So here you can see this is the air compressor cylinder in which the air is compressed. So there is air in and air out is there. That means matter is entering into the system and crossing the system. Similarly, there is a loss of heat also. In this case, there is a lot of heat also transfer also there. And motor driven compressor, as it is receiving the energy, work energy, and some part of energy may be converted also into heat loss to the outside. That means there is a transfer of energy into the system, out of the system. There is a transfer of matter or the mass into the system and out of the system. So this is the open system. Isolated system, that means simply if the boundary of the system does not permit or does not allow the matter or the energy to flow into or out of the system, this is, then it is known as isolated. Isolated means loneliness. That means it will not transfer to the outside, or it will not receive into the system anything, either the matter or it may be the energy also. So there is no transfer of matter to the outside or into the system, or there is no transfer of energy to the outside or into the system. So that's why it is the isolated system. An isolated system is one which completely unaffected by the surroundings. There is no effect on this system. If it is of fixed mass, no heat or work crosses the boundary of the system. So thermodynamic universe is the example of an isolated system. Thermodynamic universe itself, universe is the example for isolated system. Next is, what is the property of thermodynamic system? What is the property of thermodynamic system? A property of a system is an observable characteristic of the system. Property of the system is nothing but the observable characteristic of the system. The quantities which define the state of the system also called properties. The quantities or the quantity which is used to define the state of the system is called a property, or also may be written as observable characteristic of a system is also called a property, or which can define the state of the system also called a property. Right? Next, whose value must be independent of the process, and the value of the property is not depending on the process of the system, and the property is a point function. Here some of the points we must remember here are the number one, it is independent of the process, number one. Number two, it is the point function. It is the point function. Now classification of properties. The thermodynamic properties are generally divided into two classes. Number one is intensive properties. Intensive properties, and these are independent of mass of the substance. These are independent of mass of the substance. That means these properties are not going to depend on the mass of the system. So these are the independent of mass of the substance. So example is pressure. Pressure is not going to depend on the mass, temperature, density, specific gravity, specific volume, surface tension, thermal conductivity, etc. are the examples of intensive properties or intrinsic properties, you can see. These are also intensive properties, also called as intrinsic properties, right? And these are not depending on mass of the substance, that is independent of mass of the substance. Extensive properties or extrinsic properties. So these are dependent on the mass of the substance. That means they will depend on the mass of the substance. So here are the examples of the mass. Weight is also going to depend on the mass, enthalpy, entropy, internal energy, etc. Are the examples of intensive properties of the system. So once again, the properties are intensive properties and extensive properties. Intensive properties does not depend on the mass of the substance, whereas the extensive properties depends on the mass of the substance. So see, these are some of the examples for extensive properties which are going to depend on the mass. Now the state of the system. State of the system. State of the system is the condition. It is the condition and is identified through certain observable characteristics. Observable properties such as pressure, volume, temperature, density, etc. The state of the system is the condition of the system. It is the condition of the system, is called state of the system, and this will be identified by the observable properties of the system such as pressure, temperature, volume, density, etc. Right? So two independent properties are sufficient to represent the state. That means any two independent properties, maybe pressure and volume, maybe pressure and temperature, maybe volume and temperature, etc. Any two properties are sufficient to represent the state or the condition of the system. Path. So path is the series of states through which the system passes. Path is the series of states through which the system is passing. Path of a system is the series of states through which the system passes, is called as path. And say, suppose here is the initial state, here is the final state. In between these two states, there are so many independent states are there. There are so many states are there. If you join all the state points of all these, the first point and next, similarly, if you join all these, a series of states, if you join, which will be the initial state and final state, in between these two states, initial and final state, there are so many states are there. And now if you join all these points, that will be called path of the system. Path of the system. Here is the pressure volume diagram. And thermodynamic properties, process. The process, Thermodynamic process, a system is said to have undergone a process when heat and work crosses its boundaries or change the state of the system. Simply, the process is nothing but the change in the state of the system. Change in the state of the system. Thermodynamic process is nothing but the change in the state of the system, or a system is said to have undergone a process when heat and work crosses its boundaries. A system is said to have undergone a process if change of state occurs. So examples of thermodynamic process: expansion or compression of the gas. That means if it is expanded, its state will be changed. That means volume changes, pressure changes, thereby the state will be changed. And even sometimes temperature also changes. If you compress, the pressure may be increased, volume may be decreased, and temperature sometimes may be increased. So expansion or compression of gas is the nothing but a thermodynamic process. And expansion of steam through a nozzle is also thermodynamic process. And conversion of water into steam also a thermodynamic process. What is quasi-static process? What is the process during which the system remains almost in a state of thermodynamic equilibrium? The process during which the system remains almost in a state of thermodynamic equilibrium from one end state to other end state is called quasi-static process. Once again, the process during which the system remains almost in a state of thermodynamic equilibrium from one end state to other end state is called quasi-static process. A system exists in a thermodynamic equilibrium when no change in any macroscopic property is registered if the system is isolated from surroundings. Quasi-static process, here is the PV diagram, pressure volume diagram for quasi-static process, and it is the initial state and it is the final state. In between these two there are so many states are there. If all these states are in equilibrium condition, if we join all these equilibrium states, that is called quasi-static process. Static means stationary, quasi means almost. That means more or less it is remaining equilibrium. Every state, every infinitesimal state is in equilibrium. If you join all the equilibrium states from initial position to the final position, then it is called, if you join all these lines, that is called quasi-static process. If you say here in this case, this is the gas inside the cylinder and piston. If you go on heating, the gas will expand, the piston will move slowly upwards up to the stoppers. So if you say, suppose here is it remains in the same position for a small fraction of time, it may be, that is in equilibrium, and once again if you heat, still it will slowly move upwards. The initial state may be here, but it may be slowly increasing to the final state, that means up to the stopper. But every state in every unit of time is in equilibrium only, almost equilibrium. That's why every state is in equilibrium state. If you join all these states, you will get your quasi-static process. So that is the idea of quasi-static process. So what is the thermodynamic cycle? What is the thermodynamic cycle? So when a system from a given state undergoes a number of different processes, as we have discussed already, what is process, thermodynamic process. if a system undergoes a given number of different processes, one time it may be for expansion, sometimes it may be compression, sometimes it may be different. So if you join all these, and finally if you come to the initial position, then it's called cycle. That means if a system undergoes a series of thermodynamic process whose initial state is same as the final state, then it is called thermodynamic cycle. So when a system from a given state undergoes a number of different processes and finally return to its initial state, then the system is said to have undergone a cycle. Any process whose end states are identical is called a cycle. Whose end states are identical is called cycle. For example, water, that means steam, that circulates through a steam power plant undergoes a cycle. That means it will be water is converted into steam, and then steam is expanded in different equipment, and finally after condensation it will become to the once again initial state, that is water state. That's why it is gone under a thermodynamic cycle. So here you can see in the figure 4, the system has undergone a process from state 1, here is a state 1, to state 2 along a path, say let us A, and again from B 2 to 1. That means whose initial state is itself is the final state, but it is passing through one process, a process A and process B, but the final state will be the same. That's why the state 2 to state 1 along path B, the system returns to its initial state, completing a cycle. So this is the thermodynamic cycle. So now let us have the pressure of the system. It is the property number 1. Next is pressure of a gas is the force exerted per unit area. Once again, force exerted by the gas or the air or the vapor or the steam or unit area on the sides or the walls of the container due to continuous collision of gas molecules. Continuous collision of gas molecules, or otherwise simply the force normal to the unit area of surface is called pressure acting on the surface. So units of pressure are, the SI units of pressure are generally Pascal by the name of scientist Pascal, and 1 Pascal is equal to 1 Newton per meter square, and 1 kilopascal is equal to 10 to the power of 3 Newton per meter square. As the pressure definition itself is a force by cross-sectional area, and force exerted is in terms of newtons. The units for force is newtons, and then area is either millimeter square or centimeter square or meter square. So here in this case 1 Pascal is equal to 1 Newton per meter square area. That means 1 Newton of force is exerted by the gas or the system over unit area. That means 1 Pascal is equal to 1 Newton per meter square, and 1 kilopascal is equal to 10 to the power of 3 Newton per meter square, and 1 megapascal is equal to 10 to the power of 6 Newton per meter square, and 1 gigapascal is equal to 10 to the power of 9 Newton per meter square. And additional units of pressure are bar and atmospheric pressure. And 1 bar is equal to 10 to the power of 5 Newton per millimeter square, 100 kilonewton per meter square, or 100 kilopascals. And similarly, 1 atmospheric pressure is equal to 720 mm of Hg, or also equal to 1.01325 bar. An atmospheric pressure is equal to 760 mm of Hg, or 1.01325 bar. So these are the units of pressure. Now the atmospheric pressure. The normal force exerted by the atmospheric air on unit system area is called atmospheric pressure. And atmospheric pressure is measured by the mercury barometer. And the standard atmospheric pressure is taken as 760 millimeters of mercury, Hg. And 760 mm of Hg is equal to 1.01325 bar, or 101.325 kilonewton per meter square, or 101.325 kPa, kilopascals. So these are the units for atmospheric pressure. Gauge pressure. The pressure recorded by the instrument pressure gauge above the atmosphere is called gauge pressure. So the gauge measures the difference between fluid pressure and pressure of fluid surrounding to the gauge, generally air, let it be. And vacuum pressure. When pressure of the system is less than atmospheric pressure, and the gauge reads on the negative side of the atmospheric pressure. This pressure is known as vacuum or negative pressure. So absolute zero pressure will occur when molecules momentum is zero. Such a situation occurs only when there is a perfect vacuum. The pressure measured from this level is called absolute pressure. Absolute pressure is obtained by the following relations. Absolute pressure is equal to atmospheric pressure plus gauge pressure, and P absolute is equal to P atmospheric plus P gauge pressure. Absolute pressure is equal to, if it is vacuum pressure, then atmospheric pressure minus vacuum pressure. So P absolute pressure P atmospheric minus P vacuum, and then volume. Volume is nothing but the space occupied by the substance, and space occupied by the substance. The unit volume per unit mass of the substance is called specific volume. The volume per unit mass of substance is called specific volume, and the units per volume are meter cube or either liters. And specific volume is equal to meter cube per kg per unit mass. And 10 power of 3 liters, that means 1000 liters is equal to 1 meter cube, and 1 liter is equal to 10 to the power of minus 3 meter cube. Now last one is the density. Density is the reciprocal of specific volume, that is mass per unit area. Density rho is equal to 1 by V, or mass by volume, which is in units per density is kg per meter cube, where m is the mass of the substance, V is the specific volume, and capital V is the volume of the substance. Now last one, summary of this lesson. In this lesson we have discussed about what is meant by thermodynamics, what is meant by thermal engineering, and what is meant by system, and what is meant by what are the classification of systems, and also different properties, that means property of the system, different types of properties are there, and state, path, etc., quasi-static process, etc. And also some properties like pressure, volume, and density also we have discussed. Let us see the summary of this lesson. In this lesson we have discussed about thermodynamic system, types of thermodynamic systems, and examples of thermodynamic systems, state, path, process of the thermodynamic system, quasi-static process, thermodynamic cycle, and thermodynamic properties also we have discussed about. And in this lesson, once again, classification of properties, definition of term pressure, atmospheric pressure, gauge pressure, define the term volume, and finally definition of the specific volume. So far we have completed up to this and also density of the system. And let us have some small quiz questions here in this. The thermodynamic system may be defined as the matter upon which attention is focused for study if it is only bounded by real surfaces, it is not bounded by imaginary surface, the bounded surface or contact in the shape and volume, and it is bounded by either real surfaces or imaginary surface irrespective of shape and volume, which is the right answer. So last one, D, is the right answer. It is bounded by either real surface or imaginary surface irrespective of shape and or volume. Next question 2, with neither mass nor energy is allowed across the boundary of a system is called, it is called as neither mass nor energy. It means no mass transfer, no energy transfer. And what type of system it is? Closed system, open system, and isolated system, and none of the above. So as we are already three types of systems, we are having closed system, only energy crosses the boundary, no mass transfer, and open system, both energy and mass will crosses the boundary, and isolated system only no transfer of mass and no transfer of energy. So that's why C should be the right answer. And third one, a centrifugal fan forms closed system, open system, isolated system, and none of the above. A centrifugal fan forms, let us see the answer here in this case. And this centrifugal fan is just like transfer both energy as well as the what we call mass also. That's why it is open system. Fourth quiz. Identify the property among the following: mass, pressure, weight, none of the above. Which one is not? Which one is the property? Mass is not the property. Pressure is the property of the system. Weight is not the property. None of them is not answer. That's why B will be the right answer. Quiz 5. Identify the intensive property: pressure, temperature, specific volume, and all the above. Here are the intensive properties or intrinsic properties. Pressure is also same, temperature is also same, specific one, because all these are not depending on the mass of the substance. That means system. That's why all the way is the right answer. Sixth page. Identify extensive property, extrinsic property, specific gravity, enthalpy, specific enthalpy, and specific volume. This, if there is a specific, then it is simply intensive property. Only the enthalpy is the extensive property. Thank you for patient hearing of this lesson. Thank you one and all.